Hello everyone. In this video, we will learn how to compute arc length of parametric curves. I will just write down the result you need to know, and then we will discuss on some few points that may clear out why that formula works. So we have a parametric curve, so consider a parametric curve defined by parametric equations like x is function of t, y is function of t, and we consider the part going from a to b. Then if x and y are differentiable with a continuous derivative, then the arc length of the curve is going to be given by this integral a to b of square root of the derivative of x squared plus derivative of y squared, added them, find under the square, put them under the square root, dt. Here you may say that, okay, where that formula comes from. So that is the formula you need to know. By the way, you don't need to be worried about the limits of the integral. Just put the smaller value for t in the lower and upper value for the bigger value in the upper limit. Okay, so the reason, well, I'm not going to show this whole formula where it comes from, but the main part is coming from this fact. So if you have a curve, then you can divide it into small pieces. So I would say that, okay, at some point there's a tk, and then at tk plus delta t is there. And then I instead of taking the whole curve between these two, I can consider the straight line connecting two endpoints. Note that here the point there is going to be x at tk plus delta t and y at tk plus delta t. And here at this point is x at tk and y at tk. Now we want to find the length of that straight line. Here we can simply form the right triangle. And you notice that, okay, so this side of that is going to be the differences of y. So y at tk plus delta t minus y at tk. And this one here is going to be x at tk plus delta t minus x at tk. Well, if you have those ones, automatically that line is going to be equal to, the length of that is going to be x squared, well, this piece squared, let me write that one as delta x plus delta y squared. And well, you can add all those pieces to find the arc length, but then what we do here is that you multiply this square root by delta t and you divide the square root by delta t. But if I take the delta t inside, that's going to be delta t squared inside the square root. So this is this guy plus delta y squared, and then I can separate these ones, right? Delta x divided by delta t squared plus delta y divided by delta t squared times delta t. Now you have to add all those things. There are some works to do, but when t goes to 0, oh, sorry, delta t goes to 0, what happens is that this guy turns to derivative of x at that point squared, and the second one will turn to derivative of y at that point squared. And you have this square root of that. While this delta t, in the process of letting delta t go to 0, will go and play the role of delta t dt for the integral. This is not a proof. This is just giving you an idea where this sums of squares of the derivatives of x and y comes from. This is basically Pythagorean theorem applied infinitesimally on this curve. Okay, let's do an example. Find the perimeter of the circle of radius a. So I'll start with a parametrization. So a cosine t, y is b a sine t, and t here goes from 0 to 2 pi to go around the circle once. Now, the arc length is given by integral 0 to 2 pi, derivative of x squared, derivative of y squared, dt. And this is derivative of x is minus a sine t. Derivative of y is a cosine t. And if you factor out a squared there, this is going to be a squared sine squared t plus cosine squared t. But that is our friend 1. So I have 0 to 2 pi of root of a squared times 1 dt, and that is just a t go from 0 to 2 pi, which is 2 pi times a. That is the circumference of the circle. 2 pi a is there. Let me finish this video by one remark. So recall that when we are working with the graph of a function, so we have y equal to f of x. In that case, the arc length, we did have this long time ago. It was from go from a to b of 1 plus f prime at x squared dx. You may wonder, what is the relation between these two formulas? Now we have a formula for the parametric one, and we have a formula for the graph of function. Well, this can be obtained, maybe I should write in black. This formula can be obtained by parametrizing the function, the graph of function. Remember, there are more than one way to do this, but the easiest one is that set a t to be your parameter, then y is going to be f at t. Then integral from a to b of derivative of x with respect to t, so d of yes, so let me write it like that, dt of t prime squared, sorry, dt of ft squared dt. But you see the derivative of t with respect to is 1, so you have 1 squared, which is 1. Derivative of f with respect to t, we write it by f prime t squared dt. Go from a to b. And this is exactly the formula. What I'm trying to say is that the formula here we gave for the parametric curves actually implies the other formula, gives us the other formula that we have for the graphs of a function.